let's start. So we started off with noise last class. So we looked at the noise in a resistor. We looked at filtered noise from a resistor through a capacitor. Okay. So in this class, today's class, we'll see what are the noise sources you have in transistors, particularly MOSFETs. We'll look at MOSFETs. You can look up bipolars. Bipolars is pretty straightforward. Okay, so we'll particularly go through MOSFETs. So the first kind of noise we're interested in is called thermal noise. Okay, similar to thermal noise in a resistor, you'll also have thermal noise in a MOSFET. And depending on the operating region of the MOSFET, the noise will change. Okay, so let's first consider what happens if you're in triode. What do you think the noise is going to be when it's off? Of course, zero, right? There's no current, there's no noise. But in triode region and in saturation region, you're going to have some noise, and the two noises are going to be slightly different. So if you write the equation of the transistor, in triode region, okay, what we can do is we can find out the impedance of the MOSFET in triode region, which is dou ID over dou VDS. What is this? K prime W over L into VGS minus VT minus VDS. Okay. Now for very small VDS, you can approximate the GD by GD naught, which is the impedance around the origin. It's just K prime W over L into VGS minus VT. Okay. So remember that in the triode region, the MOSFET behaves like a resistor, at least for small voltages. Okay. So what do you expect the noise to be? For a resistor, it's 4 kT R delta F, or the current noise is 4 kT over R delta F. Similarly, for this, it's going to be 4 kT GD naught delta F. So the current noise, right? Because there is, so normally for the MOSFET, because you're interested in, the output is in current form, you're interested in the current noise. So the output current noise is going to be 4 kT GD naught delta F. Okay. Okay. We are going to write it in a slightly different form. So we are going to write it as four kT gamma GD naught delta F, and we're going to say gamma equals 1 in triode. Okay. The reason we want to do that is because you will find that the noise of the MOSFET in the saturation region also has a similar form. Okay. Okay, so let's consider a long channel device in saturation and find out the noise. Okay, you can show that this also has the same form as that in the triode region, except there's a small difference. Gamma is 2/3 in the saturation region. Okay. How about GD naught? If you look at the equation of the transistor in saturation, and then you look at the GM of the transistor, what is that? K prime W over L VGS minus VT, which happens to be equal to GD naught. Okay. And normally you are interested in the parameter GM in saturation rather than GD naught. Okay. So it's customary to write the noise in terms of GM rather than GD naught. Okay. Okay, so this is the noise of a long channel MOSFET in saturation region. Okay, so the output noise, drain noise current, thermal noise current squared is 4 kT 2/3 GM delta F. Yes. GD naught is the impedance of the, in triode region, it is the impedance of the MOSFET between the drain and the source at the origin. Okay, for VDS, for very small VDS, right? So that turns out to be K prime W over L into VGS minus VT. Okay, now remember that this is just a convenient way. Next we are going to look at a short channel transistor. This writing it at 4 kT 2/3 GM delta F is a convenient way because for long channel devices you know gamma is 2/3 from measurements, and you know that for a long channel device which obeys the square law, GM is the same as GD naught. And typically GM is the parameter you are interested in. If you are going to design for a particular gain, you are going to design for a particular GM, in which case you need to know what the noise is, and it's convenient to write it in terms of GM. Okay, so this is typically what you will use for long channel MOSFETs. However, it turns out for short channel devices, okay, of course, the 4 kT gamma, GD naught delta F is still the expression. Okay. However, gamma now happens to be much greater than 2/3. So it can be large enough. So unfortunately there is no particular consensus on how large gamma is because it's an empirical factor. Okay. For long channel MOSFETs, it's been, repeated measurements have shown that it is 2/3. For short channel MOSFETs, it's quite common to consider values of 1. So some people have measured recently and shown that it is 1. But other people have measured excess noise and they believe that it is much larger, maybe 2 or 3. Okay. So depending on, it might be an empirical factor which you need to take into account. So it might be you might need to make some noise measurements first on your process before you design. Okay. What about GD naught? For a long channel MOSFET, GD naught happen to be the same as GM. Okay. For a short channel MOSFET, to make matters worse, GD naught happens to be larger than GM. Okay, by around like 15-20%, maybe a little bit more. Okay, so it's common to write GD naught as GM over alpha, where alpha is less than 1. In most cases, you may not use, unless, it's quite rare to use minimum length devices in analog design, but you will use it occasionally, so you need to know this. Okay? Quite often, you will use longer channel devices, so this approximation is quite valid. Okay? So if you use lengths of maybe half a micron, 1 micron or something like that, you can very well go ahead and use 4 kT 2/3 GM delta F as your noise. However, if you're using 0.18 micron, 0.13 micron lengths, then you have to keep this in mind. Okay? Your measured noise, your actual noise may be much larger. Okay. Now, sorry, this should be C. The other kind of noise you're interested in the MOSFET is called flicker noise. It's also called 1 over F noise. Can anybody guess why it's called 1 over F noise? Yeah, the power spectral density happens to be proportional to 1 over F. Okay. So if you look at this expression, some empirical factor K, so which you have to determine from measurements, over F times GM squared over WL Cox squared times delta F. Okay, this is the noise power. Okay, so it goes as, so what do you see immediately? This K is an empirical factor, but as frequency of interest increases, the noise keeps reducing. So in other words, this noise is very prominent at very low frequencies, around DC, several, up to maybe several, maybe even tens of megahertz. Okay, but not much more than that. What is the other thing? You see it has some relation on GM, W, L and so on. Okay, you can rewrite this slightly differently. Okay, some other K prime, shall we say. Right, because you know GM over CGS is omega T, so this is the area of the device W times L. Okay, so you can rewrite it slightly differently also, if it makes, if you're able to get some intuition out of it, that's good. But the primary thing you need to remember, suppose what would you do if you want to minimize, let's say you're designing an amplifier, but, okay, and you have a certain noise, you have very large flicker noise. How would you minimize it? It might be easier to use this one, right, apart from this. This one gives you, expressions in terms of omega T and area and so on, but maybe this is the one which might prove useful in general, right, when you're designing circuits. So what do you think you would do? Right? These are the, Cox is of course a circuit, it's a process parameter. You can't do anything about that. What are the two things you can change? You can change GM and you can change W times L, which is the area, right? Do you want to change GM? If you change GM, you change the gain of the amplifier. So you don't want to change GM. So in other words, you want to change W and L. So GM depends on W over L. So let us say if you double W and double L, you'll have the same GM, but your area becomes 4 times. So your flicker noise becomes 1/4. Right? So that is what you would do if you want to minimize flicker noise. Okay? Yes. Exactly. So obviously this is valid only till a certain point. Beyond that, yeah, remember that it's very hard to make measurements as you get closer because you need a very long interval time. What is DC? DC means an infinitely averaged value, right? You can never do that. So if you want to measure, at lower and lower frequencies, you have to average it longer and longer and longer, which becomes more and more difficult. So what you can do is average to a point where it's practical. Okay. So what does practical mean? If you are designing a circuit and the circuit itself will, tell you what DC means, right? It just means how long your observation averaging interval is, right? You can, perform measurements based on where you expect to use it. Okay. Okay. Now the lower expression, the reason we wrote it this way is because if you look at a device for the same area, if your omega T is larger, your 1 over F noise actually gets worse. Okay. So for example, this also shows that most probably, even though this is a process dependent parameter, you know that if you scale process from one process to the other, omega t gets much better, right? Goes as 1 over L squared, which means that it's quite possible that your flicker noise could get worse as you get smaller and smaller devices. Okay? Okay? Now, if you look at the thermal noise, it depends on the GM, GD naught of the device, which depends on VGF minus VT and so on, right? And there is no direct difference between, as long as you design for the same GM, there is no direct difference between NMOSs and PMOS transistors, right? If you're going to design an PMOS based amplifier, you design for a particular GM, it has 4 kT 2/3 GM delta F. Okay, that's the noise power. However, for flicker noise, there is a difference between the NMOS and the PMOS, because flicker noise basically originates from charge carriers, random trapping of charge carriers near the oxide and silicon interface. Okay, since the device itself is different between the NMOS and the PMOS, they use a separate channel called a buried channel. So there is a difference between the K values between the NMOS and the PMOS. Okay. So happens that Kp is approximately, you'll see it will be somewhere around 10 power minus 28. It could be even an order of magnitude different, but this will be the kind of numbers you're looking at. The difference basically, okay, I don't want to do it in class because we have to do this, but the basic difference arises because of actually device level behavior difference. Okay, so in PMOSs, they actually add an extra process step so that which pushes the channel below the oxide and silicon interface, whereas for NMOS that's not done. Okay, which means the chance in a PMOS, the chances of charge carriers getting trapped in these interfaces becomes lower and lower than an NMOS. Okay, that is a fundamental reason that PMOS is actually better than NMOS. But you have to remember, these are only approximate values. You will have to look at your particular process and characterize it to see if PMOS really is 50 times better. Maybe it's not 50 times better. Maybe it's only 10 times better. Okay, but in general it will be better. Okay. So for a MOSFET, if you plot the total IN squared, the total current noise as a function of frequency, what is it going to look like? So let's say you plot it in the log scale. You're going to have something like this. This is thermal noise. This is flicker noise. And at some point, your flicker noise is going to go below your thermal noise floor, which means it doesn't become, it becomes insignificant compared to your thermal noise. Let's call this FC. You can calculate, right? You can equate the two, find out where one goes below the other. You can show that this is approximately this K 1 over F by 4 kT gamma times Ft. So now definitely in analog circuits, this is the band of interest, right? From anywhere from DC to several, hundreds of megahertz probably, tens or hundreds of megahertz. So you are definitely interested in flicker noise, is very important. There are circuits which operate only in the higher frequency ranges where it's not very, it may seem, if you have band pass circuits which are operating here, it may seem that it's not very important. But turns out, if you have nonlinear behavior, you can have noise going from this frequency to higher frequencies. Okay, when you have nonlinear or time variant behaviors, what you'll find is, you'll find noise, weird phenomenon like noise folding over. In this case, you only have 4 kT, gamma GD naught delta F. But if you have certain kinds of behavior, you can find the noise levels actually increasing because you have noise from other frequencies folding over. We won't go through that because we want to deal with small signal linear circuits in this course at least. right? So we won't deal with that. But if you look at large signal circuits, RF circuits, you will tend to see this kind of behavior. Okay. This should be, okay, let me call it 2. So that is as far as MOSFET noise is concerned. There is one more kind of noise which is frequency dependent, which is irrelevant for this course. Okay, if you find it, I think it's called gate noise. So there is a phenomenon where you have at the higher frequencies it becomes very significant. We won't cover that in this course. Now, in diodes, if you see any diode which is carrying a DC current, that also exhibits some thermal noise. Okay. This also, yeah. So this is white noise, and its value happens to be proportional to the DC current. Q is the electronic charge. Okay. So if you look at bipolar transistors, you will be using this. Remember that you have two junctions, right? So typically this kind of short noise is prominent in diodes and bipolar transistors. Okay. Okay, so now we have looked at the sources of noise in a circuit. Now suppose you have a very complex circuit, you want to, and a network of resistors, and transistors, and you have two such networks, you want to characterize, let's say you have two amplifiers. You want to characterize their noise behavior, right? How would you characterize their noise behavior? So normally you want to look at, let's say, signal to noise ratios, that is one way. So in terms of circuits, we tend to represent it as, so let us say this is some two-port network. Okay, you're going to convert it into a noiseless two-port with an equivalent noise voltage and an equivalent noise current at the input, a shunt noise current and a series noise voltage. Okay. Call this En squared and In squared. So there are two questions. Good question. So why both of them? Because what you'll find is, in general, you want to represent the noise of the two-port independent of the impedance. So this, if you look at any practical circuit, it probably has a finite input impedance and a finite source impedance, and you want this noise equivalent circuit to be valid for all impedance levels. Okay. Simple example: if you just have En, right? If you have an open circuit at the input or a very large impedance, it seems as if you have an open circuit, there is no noise current flowing out, so you won't see any noise at the output, right? Or if you just represent it only by In alone, if you have a short circuit here, which means you're driving it with a very low impedance source, then all the noise current will flow through this. It will look as if the two-port is noiseless. So you can show from linear circuit theory that you need two of these are necessary. I mean, these two sources are necessary and sufficient to represent the noise of the two-port. Okay. Okay. Now, why do we want to do it at the input and not at the output? Because, let's take a simple example. Let's take a noisy circuit cascaded with a noiseless amplifier. So let's say this has a circuit, a certain noise at the output of its, at the output Vn squared. So the noise at the overall output will be A squared times Vn squared. It seems as if the noise level is going higher, but in reality you have to remember that the signal level is also getting gained up. The signal power is also getting gained up by A squared, So in reality, there is no degradation in SNR. Okay. So looking at noise levels at the output is not the best way to compare different circuits. So that's why you want to do it at the input, where you are taking into account all the gains. Okay. Now, you have to keep in mind that these two sources are not real sources. They are just representations of the noise. If you actually measure the noise here, you won't get any noise. All the noise happens at the output, right? This is just a so-called input referred noise. So these are called input referred noise sources, okay, or input referred equivalent noise sources, and they are just fictitious sources. If you really had a circuit, you would normally, the right way to do it is measure the noise at the output. And then you can, divide down by the gain if you want and refer it at the input. Okay. Let us say you're trying to find out En and In. In general, you'll find that En and In both have components from the same noise sources inside. So inside here you may have 5, 10, how many ever noise sources, thousands of noise sources. And when you try to calculate En and In, you'll find that there are components from the same noise source inside appearing in both En and In. Okay. So what that means is, in general, En and In are going to be correlated. Okay, partially correlated. Not completely correlated, so let's say partially correlated. Okay, so let's do one thing. Let's take an example and try to go through it. So today we'll just go through a simple resistive circuit. Okay, go through the example of finding En and In. Maybe next class we'll take a MOSFET based circuit and do the same thing. So let us say this is your 2-port V in and V out. So let us say this consists of R1, R2 and R3. Okay, this is a very simple resistive circuit. So if you draw the noise sources for this, so what we're going to do is, there are some cases, remember, that the noise of the resistor can be represented as the equivalent parallel shunt noise current source, which is 4 kT over R delta F, and the series noise source, which is 4 kT R delta F, a voltage source. Right? You can use either one. In this case, what I'll do is, for the shunt resistors, I'll use the noise. For the series resistors, I'll use the voltage. But for this simple circuit, it doesn't make a difference. Okay. Then there are also other things you can do to make your life simple. One thing you can do, obviously the noise equivalent has to be valid for all impedance levels at the output. Okay. So what we'll do is, to make life easier for us, okay, so this is ground 1 port. What we'll do is, we'll ground the output ports, okay, and calculate the short circuit current, noise current, through that short. Okay, that is just to make life easier for us, because what you'll find is it makes the network simpler here at the output side. But you can also find the open circuit noise voltage, for example, doesn't matter. So this is the same as right? This has to be equivalent to, you have two equivalent sources and a noiseless 2 port, which is R1, R2, R3, right? So one easy way to actually calculate this for any 2 port is to look at what happens when you short the input and what happens when you open circuit the input. Why do we want to do this? Because when you short the input, what happens when you short the input for this 2 port? All the noise current from IN squared will flow into this short circuit. So none of it will flow to the output. So for the equivalent circuit, the output noise will all be only from EN squared. Okay. Next we'll consider what happens when you open circuit the input. What happens? You won't get any noise current from this because it's open. All this noise will flow through the output. So output noise will be only in terms of IN squared, because that is what we want to find, right? We want to find IN squared and EN squared. Okay. Let us go back to, so let's call this A and let's call this B. The two noise currents have to be equal. What is the noise current in A? So what you're doing is, you're shorting this input. Okay. What happens with this noise current? Flows through this short circuit. So none of it appears to the output. First of all, how do you analyze this? You have to analyze it using superposition. Why? Because since these are 3 independent resistors, these 3 noise sources are completely uncorrelated. Okay. So you take one by one and you can add the overall noise powers at the output. So let's take 4 kT R over R1 delta F. That current flows through this, so it is 0 due to that. How about this current, 4 kT over R3 delta F? That flows completely through the output, right? So you're definitely going to have one component that is one component of the noise current. How about this noise voltage? The what? Okay. Okay. There shouldn't be any current through R3. But remember that this equivalent noise was in parallel with R3. Right? Okay. If I redraw the equivalent circuit for you, suppose R3 was this way. Suppose you redrew the equivalent circuit in terms of the noise. You can clearly see that there is going to be a noise current. Right? What is this noise voltage? Now due to R2, the noise current due to R2. So this voltage is 4 kT R2 delta F over R2 squared. So this side is shorted, this side is also shorted. So the noise current flowing through this is just 4 kT R2 delta F over R2 squared. So it's just 4 kT over R2 delta F. Maybe. Okay. So this is the noise current. What is the noise current in the other case? When you short circuit the input, what is the noise current? It's just En squared over R2 squared, right? What is this noise current? You have En directly appearing across here, right? So it's just En squared over R2 squared. Correct? So you're going to equate these two. So that's going to give you okay. So it's 4kT R delta F, 4kT delta F times R2 squared over 1 over times 1 over R2 plus 1 over R3. Okay. So now we have found out En. Let's now find out In. Now we are going to open circuit the input. What happens when you open circuit the input? So now let's now we're going to open circuit this. Yes. Just to calculate the noise in terms of currents instead of voltages. You don't have to. You can leave it open circuit and calculate the noise voltage. You'll get exactly the same value. Okay. At the end of the day, all your shorting out the output and calculating the current makes things somewhat easy for you because you're getting rid of, for example, when you're calculating, currents coming out from here, all of it directly flows there. That's all. Okay. If you calculate in terms of voltage, obviously the currents will be different, and you have to multiply it by this impedance. You'll see that it gives you the same values. Okay. So that's the 4kT over R1 delta F. That's the noise due to this when you open circuit this. That, okay, flows through this and this. Correct? Times R1 by R1 plus R2 the whole squared. Okay? That is a component of noise from the resistor R1. Okay? How about, actually let's try this one first, it's easier. Obviously, all this noise flows through to the output. How about noise from R2? It's just 4kT R2 delta F over R1 plus R2 the whole squared. This is a noise in A. What is it for the 2-port? Now En is completely gone. Okay. What is the output noise? Right? It's In squared times R1 by R1 plus R2 the whole squared. Okay. Again you equate these two numbers, you can get In. Okay. So what is this? If you multiply this by R1 over R1 plus R2 the whole squared. What does that give you? Okay, let's start off one by one. This one just gives you, that's the first term, plus, what is the second term? 4 kt times R1 plus R2 the whole squared over R1 R2 squared R3. Sorry, R1 squared R3 delta F plus the last one. It's just okay. So now you have calculated En, In, and now you have calculated the noise equivalent of the two port. Suppose you want to calculate in general, if you want to calculate noise, what you'll have to do is, you have to be a little bit careful with this, because so far you have not looked at what is the correlation between these two. Okay. Now, once you have represented all in terms of all these impedances, you don't even know which noise came from where. Okay. So in general, you have to be careful. This we just went through it because we want to find out what the overall noise is. Okay. But you may want to keep it in terms of, let's say you have IN R1 squared, IN R2 squared, EN R2 squared, and IN R3 squared. Keep it in terms of those. Find out EN and IN in terms of the three noise sources separately. That will tell you the correlation. Right? That will tell you how much of whether you have noise sources from both R1, R2, and all of these three. You know which portion of the noise comes from what. Okay. Yes. Okay. So we calculated this. Okay. So suppose you have, I gave you R1 was 1K, R2 was 5K, and R3 was 2K, right? You just calculate the overall noise. You'll just get for En squared, you'll get so many volts squared. For IN squared, you'll get so many ampere squared. Okay. Well and good. What this does not tell you is the correlation between the two. Okay, if we just calculate the equivalent noise source and noise voltage and noise current, it doesn't give you the correlation. If you really want to know the correlation, you'll have to be careful in not calculating it in terms of just, you'll have to calculate, instead of taking this as 4 kt R2 delta F, you'll have to take it as, let's say, En R2 squared. Adding the powers. Whereas, if you had to do it that way, you would take it, just assume that it's a noise voltage En R2, let's say, for R2. Calculate what is the component going to the current, calculate the component going to the voltage. That will give you the measure of correlation between the two. Okay. In general, okay, so in general, both En and In, right, are going to be functions of, you're going to have a component from, from R1, R2, R3, and this one is going to have R1, R2, R3. If you want to find the correlation, you'll have to, take the dot product and, divide the magnitude and so on. That will give you the correlation coefficient. Right? You remember, I'm sure you remember that from your, right? So, obviously, when these two noise voltages are not correlated, the dot product is 0. If they're completely correlated, the dot product is 1. Then you have to take into account the signs now, because here we have just considered powers. If you're doing it, if you want to find out the correlations, what you'll do is you'll assume certain directions. You can assume either one direction. Okay, it doesn't matter because it's a power, but you're going to assume an instantaneous direction for all these three. Assume the same direction when you're calculating voltage and current. And if you get a negative sign, you have to subtract. If you get a positive sign, you have to add. Just remember that for correlation. Okay. You would want the correlation because if you have a two-port and see, normally if you get if you buy a part from outside, quite often, people might specify the noise in terms of the voltage and the current. But the correlation factor matters a lot, right? If they're completely, the noise performance of the circuit itself, this is just a representation at the input. The actual noise performance will depend on whether they're correlated or not, because you are interested in the overall noise performance at the output, right? If these are correlated partially, then when it goes to the output, you'll have to correlate and add the powers. I mean, you may not be able to add the powers directly. That is the idea. Okay? You may have to, I mean, you will have to keep track of the signs.
So if they are correlated, the real noise is actually lower.
Well, depends, right? It depends on whether it's positive correlation or negative correlation, right? In the case of a simple resistor, it's probably going to be lower. Well, I don't know what you mean by lower, but instead of adding directly, that it will be lower than the sum of the two. That is true. But if you have, for example, if you have negative gains in the circuit, that is not so obvious, right? Right? If you take transistor-based circuits where the gains can be negative or positive through different paths, and quite often, you may perfectly well have multiple paths for this, for the noise to travel through the circuit. Okay, and that is when you really have to worry about correlation normally. Okay.
But generally, you can't apply so much power. You can't add power.
Which is why when you're keeping track of the correlation, you assume a certain direction and you assume a certain noise voltage and noise current rather than noise powers. And then you can add and subtract the voltages. The square of that will be the overall noise power.
When you noise voltage, noise power is coming out, then noise voltage, noise current is coming out, and then we calculate power.
Yeah, just square it will give you the power, right? It's just En versus En squared. One of them is the root mean squared, other is the mean squared.